Let us talk about this problem. We are given an infinite sized sorted array and an element to be searched in it. If the element is present in the array, then we need to return index of it, otherwise we need to return -1. Let's understand the problem with these examples. We have a sorted infinite sized array. I've used ... to indicate infinite sized, and the element that we are searching is 100. So 100 is present at index 0, 1, 2, 3, 4, 5, 6, 7, right? So our output is 7. Now let's see 50 in this array. 50 is not present in this array, right? So our output is -1. We can easily see 50 is not present because 40 and 100 are there and it is a sorted array. So if 50 was there, it must have been there between 40 and 100. So this is the problem. Now you must be wondering, how would somebody set up a question in an online contest? Because if you're programming in Java, you can get the array.length and you can find out how many elements this array has. And if you're programming in C++ and if somebody has set up a question where you are given a vector, you can do vector.size. The thing is, we can set up a question like this in an online contest where we specify size of arrays as millions. We put millions of elements in the array and we give you search inputs which are close to the left side, So if you write a program which is taking time in terms of millions, you will get TLE, right? If you write a program which is taking in terms of position of the element, then only it would work. So these are the hints to solve the problem. Now please pause this video and try to think of a solution to solve the problem. We are going to talk about two solutions to solve the problem. One is naive solution, which is big O of position. Position is the position where element is present. In this example, position is 8, 7 plus 1. In this example, element is not present. So what will be the position? We can say position is the position here where this element would have been inserted or would have been present if it was there. So 50, if it was there, it must have been at position 3. So position is 3. So our first solution, naive solution, is going to be big O of position or theta of position. The next solution that we are going to talk about is really interesting, and it's going to take theta of log of position. Now please pause this video and try to write down any solution first. Let us first talk about a naive solution to solve the problem. A naive solution is to traverse the array from beginning and keep on searching the element. When do you stop? You stop in two cases. If your current element in the array is present equal to the element that you are searching, or if it is greater. If it is equal, then you return I. If it is greater, then you return -1. So this is the code. We begin with I equal to 0. We run a loop while true. It's an infinite loop. And we say if array I is equal to x, then we return I. If array I is greater than x, then we return -1. And we keep on incrementing I. Let's understand this with this example. Say I'm searching for 10. So I'll begin from here. I'll come here. It's equal, so I'll return. Say I'm searching for something like 15. So what will I do? I'll compare with this, not equal. Compare with this, not equal. But these two elements are smaller. When I come here, it's not equal and this element is greater, right? So it means 15 is not present. So I'll return -1. So this is a naive solution and it has time complexity as big O of position and auxiliary space is big O of 1. Now think of a solution that works in big O of log of position. You can't directly apply binary search because when you do binary search, you need to do low plus high by 2 and you don't have high here, right? You don't know the array size. Even if you know the array size, high is really big. Somebody would set up the question like this way. So how would you solve the problem? And this is where this becomes tricky. Now a hint for you. A hint is your time complexity is log of position, right? So you get logarithmic time complexity when you divide a number by 2 or when you multiply something by 2 to read that number. So this is good enough hint. You may pause this video and try it yourself. Let us now talk about efficient approach. The idea of this efficient approach is we begin with index 1, then we go to index 2, then 4, then 8, then 16. I keep doing it while current element is smaller than x. When do I stop? If current element either becomes equal to x or greater than x. So let's understand the approach with this example. Let's say we have this array and we're searching for 100. So let's explicitly handle the case 0. If this is equal to 0, then I'll return 0, otherwise I'll begin with index 1. Why am I explicitly handling the case 0? Because I need to double the indexes, right? So if I begin with 0, then it will be 0 into 2, 0 into 2, which will be 0, right? So I begin with index 1. After explicitly comparing the element 100 with this 1 and they are not same, so I'll begin with 1. So what I'll do is I'll compare 100 with 10. It's smaller than 100, right? 10 is smaller than 100. So I know that 100 must be present somewhere on the right side. So instead of linearly going to the right side, I double the indexes. So I now go to index 1 into 2, 2, which is 15. So 15 is again smaller than 100. So I'll again double the indexes and I'll go to the index 4, which is 40 element. 40 is still smaller than 100. So I'll again double the indexes and I'll go to the index 8, 5, 6, 7, 8. And at this point, I find an element which is greater than 100. So I know if 100 is present, it must be on the left side of this 200, right? Because I am here and I find an element which is greater than 100, it must be from 0 to this index. Now, it's not only 0 to this index, we can further reduce the range. We can say it must be from this 60 to this 100, this index, because we have gone till this point and this was smaller than 100, right? So the element to be searched must be from 60 to this index, which is index 5 to index 7, right? It must be between 5 and 7. So I can do this optimization and I can do binary search from here to here. So this is the idea. You double the indexes, you find an element which is either equal or greater. If you find an element which is greater, then you do binary search between the half of the current value of that index and current index. So let's take a look at the implementation. If array 0 is equal to x, then we return 0. If otherwise, we do doubling of the indexes. We begin with I equal to 1 and we say if while array I is smaller than x, then we do I equal to I into 2. We come out of the loop when array I becomes equal to x or array I is greater than x in these two cases. If it is equal to x, then we return I, and if it is greater than x, then we do binary search. As I said earlier, I'll do binary search from this index to this index. In fact, I can do an optimization here. I can do binary search from this to this because I've already checked with I, right? So I can do binary search from I by 2 plus 1 to I minus 1. I came out here because array I was not equal to x, it was greater than x, right? So I can do from I by 2 plus 1 to I minus 1. So I do binary search from this index to this index, right? And this binary search is going to take log time. Now, what is the overall time complexity of this solution? Say if element is present at any position, right? And then an upper bound on the position till which you will go is 2 of position. If element is present at index 5, then you will go up to 8. If element is present at say 9, then you will go up to 16. So it's slightly less than twice of 9, but we can say upper bounded by 2 of position. So 2 of position is the position, is the index till which we will go if element is present at pos, right? Then how much time we take to reach this value? See, if you are beginning a number with 1 and if you want to reach a number x and you are doing doubling, then how much time you will take to reach x? It's log of x, right? So to reach this 2 of position, we will take log of 2 of position. And I can take the constant out and I can say it's log of position. It's an upper bound, right? It's not exactly 2 of position, it's an upper bound. So log of position time is taken by this loop, right? And this position must be from I by 2 plus 1 to I minus 1. And these number of elements between these two ranges must be less than position. So again we are going to take big O of log position time to do the binary search, right? So overall time complexity taken by log position plus log position in the worst case. which is big O of log of position. So the time complexity of this solution is log of position, and we have done in this much time in an infinite sized array where we cannot apply direct binary search. And this algorithm is commonly known as unbounded binary search.